All right, so let's talk about the atmosphere. So I mentioned it's got this low density. The low density actually reflects the fact that it's mostly hydrogen gas, hydrogen molecular gas, H2. So this is actually the first time we're seeing a planet in the solar system which was able to hold on to its primordial primary atmosphere. Let's look at the hydrogen gas here. Try to keep it to a minute. Now, we talked about how, we talked about Venus and the Earth and Mars. And we kept talking about a primordial atmosphere that was mostly hydrogen, but it gets lost, right? The hydrogen got lost with the terrestrials because they have low masses and they're close to the sun. So they have high temperatures and low masses, so the hydrogen gas is not retained. It percolates away into space. So Jupiter here is the first example of a body that's cold enough at its distance from the sun, very low temperature, and it's massive enough. I actually didn't really emphasize this, but notice if you look at the mass, it's 318 times Earth's mass. Okay? So it's cold enough and massive enough to hold on to that primary atmosphere. First example of an object that is able to do that. So what we're really seeing when we look at Jupiter is basically its primordial composition. It really hasn't changed that much because it held on to all its primordial gases, and this is what you get when you do that. You have mostly hydrogen, over 85%, quite a lot of helium. These abundances here are actually similar to the abundances in the sun itself, which also, a body that held on to all its primordial gases. We do see evidence for water ice and ammonia ice. That actually is what gives us the different colored clouds that we see when we look at Jupiter. Okay, just contrasting with Venus here. Completely different atmosphere, obviously. Venus is mostly carbon dioxide, none of the water vapor. The primordial atmosphere is completely gone. And so, of course, we see that the primordial atmosphere is maintained on Jupiter. Basically because it's massive enough and cold enough to have retained that hydrogen gas. Looking at Mars, again, we see this mostly carbon dioxide composition. Earth, mostly nitrogen. But none of the terrestrials look anything like that Jupiter atmosphere. Okay, so here's our nice plot here. Again, our temperature pressure curve. Notice it's still the classic form, dropping as we go up in altitude and then turning around and rising again due to solar radiation exposure. Now, this is a slightly different looking altitude scale because on the terrestrial planets, the bottom of our plot was always at 0 altitude off the ground. You just start on the ground. Well, there isn't any solid surface in Jupiter, essentially. So the bottom of the scale here is some distance below the cloud tops, but it's not the actual solid surface. We can keep going down and down for thousands of kilometers inside Jupiter, and it would still be gaseous. So the 0 of altitude is just set here at the cloud tops. Rather than any kind of planetary surface, we just set the 0 of the altitude of the cloud tops. All right, so now let's look at the temperatures. Now remember, in the case of Mars, we saw surface temperatures that were down around 250 kelvins or so. Notice here we're seeing temperatures in the upper atmosphere that are actually even below 200 kelvins, only around 150 kelvins or so at the cloud tops. Basic conclusion from that, we're farther from the sun. Remember that these temperatures are always determined by a thermal balance between solar heating and emission of infrared radiation. But at these cloud tops, at the distance that we're talking at now from the sun, 5.2 astronomical units, solar heating is very weak. So when you get that thermal balance, you're going to achieve that balance at a low temperature. And so that's why we have this around 150 Kelvin temperature at the cloud tops. It is higher as we go down inside Jupiter. That's probably due to compression effects, because the density gets a lot higher. And actually, if we look at pressures here, we see that when we drop down about 50 kilometers below the cloud heights, we start hitting Earth pressure. And then it gets much, much higher. Kind of like going underwater, you get a higher pressure, right? But we also get a higher temperature. All right, the final point to make here is that we're seeing these different colors in the clouds when we look down at Jupiter, which reflect different ices like ammonia ice and water ice have different colors, but they also exist at different altitudes, because remember that ices of different substances freeze at different temperatures, right? Here we have water ice down here. We move up colder to a higher temperature. Well, actually, look at where water ice is forming, right around 300 kelvins or so, 273 kelvins. 273 kelvins is the freezing point of water. So our temperature curve of that layer is just what you'd expect for water ice, about 273 kelvin. As we go up higher, it's colder, around 200 kelvin. That's where we're going to see ammonium hydrosulfide freeze. And then ammonia itself freezes even higher up. So when we look down at Jupiter and we're seeing different colored bands, we're actually looking down to different altitudes. Because if we see a bluish streak on Jupiter, it means we're looking down to this altitude, about 70 kilometers below the cloud height, which means that for some reason there's a hole in the cloud deck there, and there isn't any of the brownish ammonium hydrosulfide cloud. So we're able to look down through this hole and see the colder, actually the warmer layer, where the water ice is present. Okay, so the final thing about this, I haven't mentioned before, is this equilibrium temperature of the cloud height, actually it's about 125 Kelvin. That's what we're seeing as the temperature of the cloud height. But if you actually look at the amount of solar heating at that distance from the sun, 125 Kelvin, as cold as it is actually a little warmer than you expect at that distance from the sun. You actually expect about 105 kelvins at the cloud tops on Jupiter at Jupiter's distance from the sun. So this is an anomaly. You're actually seeing cloud top temperatures that are a little higher than what you expect to see. And so if you actually do the math here, remember that it's radiating energy according to Stefan's law, which means it goes like the fourth power of the temperature. So this little bit of an offset, 125 kelvin versus expected 105, that little offset, if you raise that ratio to the fourth power, you get about a factor of 2. So what that means is, at the temperature that Jupiter is, at the cloud top, 125 kelvin, it's a little hotter than the expected 105 kelvins, which would be the true equilibrium. So it's actually radiating about twice as much energy as it's receiving. At the temperature that it has, it's simply radiating more energy than it's receiving from the sun. So there's an imbalance there. And that imbalance has to be powered by some kind of a heat source, because it's not in equilibrium with solar radiation, so there has to be another way that energy is being produced inside Jupiter. So we're going to talk about a couple of ways that can happen.